that we know that the complex power junctions how to calculate the complex powers of the Y network. Okay, so that as we discussed previously, and interactive solutions is needed for the non-linear system. Okay, so in the power flow, firstly we assume that we know the complex power of the bus I and the Y matrix bars, and we like to get the value, the voltage level, or the voltage magnitude of the bus I. Okay, so for here the difficulty here is that the following nonlinear equations. Okay, so let's see that there's a nonlinear equations. We know the complex power of the bus I, and we need to calculate the voltage here. So we will to use the interactive approaches here. Okay, so let's get started. Okay, firstly we will introduce the iteration or Jacobi or anyway so the iteration method. So because it's actually there will be a large amount of the different interactive methods, and we will consider two of them, so the Gauss iteration and the Newton iterations. Okay. So firstly, the Gauss methods. We will firstly introduce the Gauss iteration methods here. So we will rewrite our equations to the forms such as the hx. Okay, so hx is a function of the input x. So that for the Gauss methods, the package here is to find the x that will satisfy these equations. Okay. Okay, because this is the nonlinear problem, so that firstly we will get an initial gas of x. Okay, so we will call the x0, so in the 0 steps, and then we will just do iteratively plot into the right hand side. Okay, so the right hand side calculate, because we can use the initial value x0. Okay, from here, and we will get the function value of the x0. Okay, to evaluate updated gas x plus v plus y is equal to the hx. Okay, so just like the x0 here, we will get the x1. Then we get the x1 here, we get new value to the x2. Then x3, x4. Okay, so the three for the interactive functions. So if we are close to a fixed point, okay, it's like we will find the x4, the x5, and 6. They are all in a very approximate value. Okay, all the approximate value. So we call it a fixed point x plus. Okay, so such that the x plus is equal to the hx. So we will stop the iteration, and we get our final solution for this problem. Okay, just one example. We would have to calculate this x minus square root of the x minus y equal to 0. Okay, so that we will first to rewrite this equation, this problems and functions here. Okay, so we assume that the hx is equal to 1 a the square root of the x. Okay, that the iterations here you can see that the x is equal to the square root of the sum of the square root of the x and the y, okay? So that we can get the iteration process such as this. So the initial function or the previous value of the x, input value x here, we can get a new function value here, okay? Then we will get the updated value of the x. Okay, so the current iterate xv, okay, into these functions and see the answer. So the value of this function of this solution, the solution will be the next iterate xv plus 1, okay? So and then we will repeat this relation until the satisfying solutions we get, okay? So that we start at the 0 step, level 1, and we guess the x0 equal to 1, okay? 0 is the first step, x equal to 1. Square root of 1 is 1, right? 1 and 1 is 2, right? 1 and 1 is 2, so that this is the first step, xv, right? Because this is 2, and we will get to the update the x value of the next step, okay? 2. And then in the second step, we will use this 2 to the function, right? 1 and the square root of 2. Square root of 2 is approximate 1.414, okay? So and plus 1 is 2.414, okay? So then we will get this value to the function, and then in the second step, the third step we'll get this, the fourth step we'll get this, 5th, 6th, 7th, 8th, 9th, okay. And we can find that, right? This is 1 and 2, 1.4, 1.5, 1.5, 1.6, 6, 6, 6, 6. You can see it will be very smaller amount of differences between these two steps, okay? Okay, so in that case you can decide whether to stop, okay, when to stop the iterations, because our solution is a much more approaching the true value, okay, the true solution of these equations, okay? Here is how the Gauss iteration is doing. So any problems and questions? Okay. Okay, so next up we will need to provide or arrange or decide a stopping criteria, actually. We can say 9, and of course we can get the 10s, 11s, 12s, 13s, maybe to 100s, okay, but there will be no necessary to get so many steps, okay, so that we will get a stopping criteria to decide when to stop the operations, okay. So we will get delta xv, the differences between this step and the previous step, okay? So differences when it is smaller than the stopping criteria here, okay? So if x is bigger and it's bigger, but if x is a vectors, so we will just to use the absolute value or magnitude of this function of the this variable to no more or smaller than the stopping criteria. Okay. So the normalization. So how to get the absolute value or the magnitude using the Euclidean or infinity. So it's up to you. Okay. So you can get the absolute value to make sure that the vector, the magnitude of the vector is smaller than the stopping criteria. Okay, so we're going back to our power flow analysis. Okay, first step, we need to put our previous equations to the appropriate form. Okay, we start to direct it to this expression, to such an expression that we know that the complex value or complex power here, right, V occurred with the quantity of current to the voltage and the sum of the Y matrix and V, okay, of the different voltage, okay, so that the time to each S is equal to this. Then the time to each X divided by V is equal to this. Okay, so the very easy relations, and then we can get the V because we know the complex power and we need to calculate the voltage. Okay, the voltage is equal to this. Okay, so that we define this. You can see the HV is the HX functions to this. So this function is the function that we need to get the iterate process. Okay. So that this is the power flow function equations that describes such as V equal to this HV, right? Okay, of course, and here is the example expressions, and you can use the other appropriate equations as you wish. Okay, so here is the example one, so that you will get initial value 0, 0, and update according to the V1 equal to the function value of the V0, and V2 equal to the function value of the V1 until the differences, the absolute value of differences is less than the stopping criteria. Okay. Okay, we'll continue our lecture 11. Okay, so let's take some pictures. The wind blade value, the thing, the wind blade should be the 3, right? Wind blade, first 1, first 2, first 3, and 3 shown here. And here is the thermal commands can fail as well, boom, right? And also the match and power, you can see this substation, right? The transformer. So
Is this fixed because damage it?
yes, boom, boom. So that's why we need to learn about our power flows. You see that every part of our power systems has risks to fail, so that we need to get a correct estimation of the top flow to make sure that the other part decide this value part to steer what where, okay? Okay, so here is the two bars system, okay? So here's an example when we will use the Gauss iteration to get the value, okay? 100 megawatt and 50 megawatt load is connected to a generator's line of line with 0.02 and 0.06J. Okay, here is 9 impedance. And then charging of 5 megabar on each end. Okay. Here is the shunt, right? Bars 1, bars 2, and also here is the shunt capacitor here. Okay. Right. And if the generator voltage is 1 pu per unit, okay? So the first thing we're just to convert this actual value to the per unit value, okay? So we assume that this node, this power is the base, okay? So that 100 meter a watt is the base value, so that the real part is 1 and the imaginary part is 0.5, the half, right, per unit. Okay, so that we're just to convert this to the per unit value. And of course, you can see that the shunt value was due to per unit 0.05, right? And for the impedance, because it is already converted to per unit.
And our voltage is also per unit V1.
So everything here is per unit value. Okay. So the unknown part, okay, so is the complex node voltage V2. So the voltage here, the voltage of the bus 2, okay. So because it's a parallel, so that the voltage of the bus 2 is the voltage of the node, right? So that we need to know the Y bars at first, okay? So the maintenance bars, the 2 and 2, because there is only 2 buses in the system, okay? Capacitor and the susceptances specified by reactive power and rated voltage, okay? That we firstly convert the line impedance to the line series admittance, okay? So inverse of the Z, inverse of this value equal to 5 minus 15J, okay?
Yes.
And then the Y bus 1, bus 2, so that the mutual admittance is a negative 9 admittance, right? Negative minus 5 is 15, 5 and 15 for these two, use difference. For this, here is bus 1, here is this 9 admittance, and here is the shunt capacitor, right? That here is the 9 admittance plus the shunt vector plus the 0.05J, right? So it is take this value. But for the bus 2, because here is 1 node here is a line transmission, line admittance. Here is a shunt capacitor here, and here is another shunt capacitor here, right? That this three, the sum of these three admittance, so that here is less than the surface admittance of the bus line. Okay. So okay, everything okay here?
Yeah.
Okay. So because we know that the bus V voltage of the bus line, the first bus line is 0, okay? So we will only need to consider one entry of the HV, okay, HQV, okay? So here are the equations to solve, right? There is the voltage and the complex power, voltage times power, and we assume that this part, this function value is equal to the HQV, right? Because the bus 1, and we know that here is the specific value, so that we only need to calculate the voltage at bus 2. So on stage, right? Y22 and S2, V2, for these. And VT here is only one term, right? V1, right? Here, so this is the one. Here is the voltage in the first bus. Okay, so we also assume that initial value V20 is also the 1, okay? So let's start. And we get the 1 here. And then we're at the first step. The first step is 1 at this. And the second step, V1, this, the 0, first step, second step, third step, fourth step. We proceed. There is almost no differences between the two, okay? So that we have arrived in the convergences of these iterations, okay? So here is the final solution of this value. Okay, so let's see, we got the fixed point, right? Let's see, the third and fourth is the standard, right? So that we got the fixed point V2 here is the value here. So as long as we get all the voltages of the all buses, so other values can be determined, okay? So the everything is the voltage below the power, so the power below, the current below, so everything we can calculate. Okay, so that the complex power of the bus 1 we can calculate. So the actual unit, this is the actual, that means the actual value, okay? So the real power, the active power, the reactive power, okay? So the capacitors can also be calculated. So any problems with this example? No? Okay, so next snack bars. So what is snack bars? You can view it as a reference bars. Okay? So because it just named the next example, we specify the complex power and voltage, or complex power of the bus 2 and the voltage of bus 1, and then we solve for the complex power of bus 1 and the voltage of bus 2. So that, and actually we cannot to specify the complex power for all and all buses because the total generation must equal to total loads and total losses. Okay, so here is called the power balance here, right? So that we also need angle references bars. Okay, so that we need to decide at the very beginning that which bars we call it the reference angle, so that is the 0 degree, right? Because at each angle is relatively phase shift, right? So that here is a reference for both the angles and the voltage for the magnitudes. So that in this case, we will define one bus as snack bars. Okay. So snack bars has a fixed power, magnitude, and angle, and varying, so that the voltage, magnitude, and angle is fixed, is unchanged. However, the real power and the reactive power injections can be changed or varying. Okay, can be vary or change to satisfy overall real and reactive power balance. Okay. In that case, that means that because all the reactive power and the real power need to be the sum of the real power of all the buses in the system should be 0, right? Because there will be how much power you send out in the network and how much power will be used in your node, right? So that select power, for one thing, is a reference to make sure that to perform the base value, just like the periodic analysis, okay? And the second thing is to make sure that the balance, the power balance, can be matched in one network or in one system. Okay? So that just like this. In these two systems, here is the snack bars. Okay? And we can note that at 0 degree, then the reference degree. So every other buses, the angle is compiled with the 0 degree. So we record it the snack bars, the magnitude is fixed, the angle is also fixed. Okay? Fixed bars. Okay. So the previous example is based on the 2 bars system, but if we need to solve for the many buses system, with the more than 2 buses, okay? But for buses, we calculate the values, the new values of the voltage VI, okay, for the I bars. You can see it's a signal, right? The only difference is the same expression, same equations of the new voltage. The only difference is that in the previous examples, the other buses is only 1 because here is only 2 buses. But for the many buses systems, you will see that V1, V2, V3, Vn, right? There will only some extra buses in this term, okay? So if we have determined the V plus 1, so the updated value, voltage value, okay? So then we do estimate the voltage at bus I rather than the V I as the previous step, okay? So that if we choose to use the latest value, so the updated value, so it's called the Gauss seidel iterations to be maybe improved version of the Gauss iterations, okay? Just like it's how the Gauss seidel iterations is working, okay? So in these iterations, it will immediately use the new voltage estimation, okay? Because we assume that the bars 1 is snack bars, you see the V1 and V. In this case, we are calculating the V2, the update, the V2, the voltage of the bus 2 is updated. However, you can see that V3, V4, Vn, this remaining voltage buses, the voltage of the buses, a not updated batch. We only know the V2, we only get the updated value of the voltage in the bus 2. But however, we will also use the new values here to calculate the V3. Okay, so in this case we know the V2 and the V3, and we use the new values here. We can do the V4, the new value of V4. So repeat all our steps to make sure that every, okay, so the voltage in every buses will be get updated, okay. So that's what is the one of the major differences between the Gauss seidel iteration and the traditional Gauss iterations, okay. So of course we have the better performances and easier to implement, okay. So any problems here?
After this point, I will go into the room. After reading, maybe I will find a problem.
Okay. So let's get some. We'll give you some examples. Okay. So the first thing, we need to define 3 main types of the buses. It's actually the PQ nodes. PQ nodes is that we know the real power P and reactive power Q, okay? So these two are known and fixed, and our goal is to solve for the unknown voltage magnitudes and angles, right? Okay, voltage magnitude, voltage angle, real power, active power. These 4 parameters we know 2 and we solve the other 2. Okay. So for the PQ nodes, we know the PQ and we solve for the voltage magnitude and the angle. Okay. So in our real world, the PQ nodes, PQ bars will generally be the nodes because we know how much power our generators, our air conditioners will be needed, right? And select bars that we have introduced previously, so that the magnitudes and angle of the voltage is fixed, and the P and Q need to solve, okay? And another type of the nodes we call this PV bus, okay? PV bus that we know the real power and the magnitude of the voltage, and we need to solve the voltage angle and Q, right? So it's quite easy to understand that PV, we know the PV to solve other two, P2, we know the P2 or to solve the other two, right? And for the PV curve, so if you use generally to describe the generators, right? If the generators, you need to know, okay, so how much power or how much useful power it can generate, right? I will not be interested to how much reactive power you need to produce, right? I need the useful part. So that in some generators, we know the P rather than Q. And of course, the voltage, because we need to connect the generator to the different network, right? And you need to make sure that the voltage of your generator is suitable for the network with the different voltage level. So that's why the PV bars is generally the generators, but for the P2, we consumers, right, we have knowing that the average part of the rectangles is 2 and 20 volt. We are not interested in the voltage magnitude, right? So only need to know the P and Q enough, because we need to know the total complex power. Okay, there are 3 parts of the nodes or buses in one system. Okay, so and making sure that select bars will only have only one bars can be selected in one system. So that should exist in one system, but only one. Okay, we cannot have 2 references. Okay, so I will give you some examples. If we need to calculate the PV buses in the Gauss-Seidel operations, okay, we will get another equations. We know that the S is complex power goes to the real and the reactive power, right?
This is conjugate, sir. This S power is conjugate.
Yeah. So that because we have known the P and the V, right? So that we only need to get the Q. Q is the imaginary part of this, right? Okay. So that this is a function that will be used in the iterative process of the Gauss-Seidel method. Okay. So here is the package functions. Okay, so we will solve for the V. Okay. Okay, let's continue our. Okay. So that in update we will get this update value of the voltage of I, right? Because the difference here is that we know the voltage of the magnitude, right? Because here this is a PV curve, this is a PV bus, we know the real power and the voltage magnitude, so that we know the magnitude here. So that we can replace this is the intermediate parameters of voltage by this. We know that. Okay, so we see that the V update value is equal to this. Let's see, because the voltage magnitude is the same, right? So no matter how many times you update, the magnitude or the absolute value will be the same. Okay, so this is the different part between the PV buses examples and the PQ buses examples. Okay. Yeah, PV, because we know the voltage, right? So the voltage should be the same. Okay. Okay, so here is the two buses system, right? The same, the line impedance, the shunt capacitors, and here is snack bars. Okay. We also know the voltage in the bus 1 is 1 per unit, and we also know the voltage bus 2 is 1.05 per unit. Okay, so
P equals 0, sir. P equals 0.
Yeah, 0, right? P2. But see that the node is replaced by the generator, but it does not produce the power. Okay, it may only consume power here. Okay, so then the reactive power of the bus 2 here. Okay, so we'll use the same equations, right? For here, it's only one bus, right? From the bus 1. So we'll get this, okay? Bus 1 and bus 2, okay? Y21 and Y22, of course, okay? This part. Okay, so that we can get the voltage in the bus 2 is equal to this, which is the standard directions. We can calculate that it's the only, let's say that Y occurs with Y neutral admittance here, right? Voltage here. So that we will use the initial value. You can see that 1.05 here is the initial value. Then the first step, we will get this V2 and the V2. This is the medial parameters and this 2 voltage of this bus 2. So that you can see for these intermediate parameters, the magnitude is approaching 1.05, but for the Q2 we know that the voltage is at the voltage magnitude is the same value here, that we are only concerned about the angles. So angles, you can see, is also approaching, is also changing, okay? Let's see, for complex power, because here there is no real power, and there's only a shunt. Okay, so the whole part, so the complex power is only about,
The imaginary part.
yeah,
The real part is 0.
no real part. Okay,
Because generator power is 0 megawatt.
okay, so any problems in the previous case or here? Okay, bigger. No? Okay, let's continue. So the generator, reactive power limit, okay? So actually for each generators, the reactive power approach to varies to maintain the terminal voltage and the real generators down by the exciters. Okay, so why, as I introduced to you in previous lectures, the reactive power, let's see, it is used to maintain the terminal voltage. Although the reactive power is not used directly by the consumer or the node, it has still useful to maintain the normal operation of the transmission network. Okay. Okay, so you can see that the higher voltage, the more reactive power. As for generators, there should be a limit for the reactive power in the real world, and also dependent on the generator's real power output. So this limit will be maybe considered as long as it is stated when we solve our power flow problems. Okay. So during the power flow, once the solution is obtained, must to check whether the reactive power output is within this limit. So if the reactive power is beyond the limits, so the phase 2, then phase 2 at the max or minimum value, and we solve the treating the generator at the PQ bus. Okay, so the tape switching. And so let's say this is a very good method to make a double check of your solutions for that. Okay?
Yes.
Okay. So the next, so we can see that convergence. So what is convergence? Do you know that?
Convergence and divergence.
Yeah, convergence. Right?
We in mathematics, convergence and divergence.
Yeah, this is called convergence. Convergence, you can just view it as a fixed point. When we start our initial value, we are approaching, and we got to the fixed point, then the convergence is completed. So that's really called to accelerate the convergence. You see that maybe in the original method we will have 10 steps of iteration, right? But if we accelerate the convergence, the pace of the convergence, maybe we will have only 5 steps to get the same fixed point. Okay? So then we call the accelerate the Gauss-Seidel convergence. Okay? So that you can see that the Gauss method, that the object value is equal to the function value of the previous x input value. Okay? And to accelerate convergence, we can rewrite this as, okay, we add an extra input value and z minus. Okay? And we introduce the acceleration parameters alpha, right? So we get the alphas here to the functional value of the previous input. If we see the alpha is equal to 1, and these two disappear, so it will be equal to the same expression, the original expression, right? So when alpha is equal to 1, so if we call the standard the Gauss-Seidel iteration, right? But the value of the alpha is, the faster the convergence will be completed. Okay? So let's see one example. So the same equations, we do solve this, and we rewrite it as this. You can see that here the alpha the accelerate coefficient, right? Okay, you can see when the alpha is equal to 1, when the alpha is equal to 1.2, 1.5 equal to 2, okay? When the alpha is equal to 1, so that this equation is the set of the original Gauss-Seidel iteration methods, okay? And you can see for the alpha is equal to 1, or get the fixed step to get this
2.618.
yeah 6118, right? And for the 1.2 it's much faster.
176.
1/2 actually fourth, and 1/2 is then 23rd, okay? So it's fluctuation. So that it's up to you to choose whether to take the acceleration coefficient here, okay? The larger the coefficient is, the faster the convergence will be completed, okay? So it's up to you to whether to choose your standard Gauss-Seidel iteration or the faster iteration, okay? So the benefits, so its iteration is relatively fast, okay? And relatively easy to implement, okay? So it is advantages and disadvantages. And to convert relatively slowly, so it can be improved with the acceleration, so has a tendency to fail to find solution. If we are doing the study for the large data, and to divide, to converge on cases with negative, fast range reactances, and to use the complex numbers in integrations, and can be easily replaced by our new methods, the Newton-Raphson methods. So would you still feel cool to continue our new?
No.
You feel tell about this, or is you feel it's too much? You meant
Today you gave us lecture 10 and 11 half already. So we have to study first. We have to give you 10 and 11. If you give us more.
Okay, of course. Okay, let's stop here. Okay.
This is page number of lecture 11, page number, this page number.
Okay, I will start to what's the Newton-Raphson, very important. So we're just to introduce the next week, okay? Okay, so you need to know this, okay? See, yeah, it's actually because it's more complex than
Yes, sir. First we review our this class.
so in definitely examination, can you calculate this one? Jacobi matrix differentiation of the differential include, and here is a matrix.
First time I differentiation this variable and find this value. After that I make integral.
Yeah, if you fail, it's difficult to calculate. Maybe a result just give you problem something this. But with Jacobi, if you or your own research work, you can use your computer, MATLAB, or calculator to use this. Okay.